for coming to our weekly seminar. I know it's a Wednesday, so we're a little off schedule there. I know people have some class conflicts, midterms, Grand Prix racing, all kinds of excitement. I know some of the people coming here today are still looking for a place to park, but I'm sure it'll be okay. I remember when Bernard Batson, who's here from the College of Engineering, came up to me and said, "Oh, we've got to have Christopher Blaszczak-Boxe come give a wonderful lecture to our program." And I said, "Tell me more about him." He goes, "Well, initially when I first met him, I thought he was a grad student giving a presentation, and I thought, wow, what an impressive graduate presentation." And then I found out he was actually a faculty member who had a long list of appointments, and I'm going to go through these appointments because it's quite impressive. At present, he's an assistant professor at the Department of Chemistry and Environmental Science at CUNY, which stands for City University of New York in Brooklyn. And he was invited by Bernard and also Frank Muller-Carter, and he's going to be giving us a talk about a mechanism for biologically induced iodine emissions from sea ice. He got his bachelor's degree in chemistry and a minor in mathematics. Pay attention, Josh. Josh was also got a degree in mathematics. He was here. Stepped out. Actually, I see ghosts sometimes. After that, he went to California, and this isn't such a bad thing for people. I grew up there. It's not a bad place. He got his master's and his PhD from Caltech in the program of environmental science and planetary science and engineering. I got that out of order, but 3 different programs at Caltech. He then went on to do a postdoc at Caltech with a JPL fellowship. These are very competitive fellowships to obtain. And he continued working at Caltech and then went on to NASA JPL and got a job there as a research scientist. So at lunch today, he had a lunch with many of the students showing the pathways to a PhD and how different ways you can get there. And he took interesting pathways. He then went to Brooklyn with his family and is now an assistant professor there. He also was, just last year, nominated as Professor of the Year National. It's a U.S. Professor Award. So that's really quite an honor. Congratulations on that. It was a very competitive process, and he got a commemorative plaque for at least being nominated, and it's clearly a sign that you value teaching as well as research, so that's great. So, without further ado, I invite you to come up here and start your presentation.
Thank you all for coming. First, I'd like to thank Bernard for inviting me, and the Marine Science faculty for organizing the visit as well. And today, I'm going to talk specifically on one topic, okay? And I'll say a few things. In 1995, we know that 3 scientists discovered, won the Nobel Prize for elucidating the mechanism for destroying what? What destroys ozone in the stratosphere, right? That was Crutzen, Molina, and Rowland, right? But today I'm going to talk about what happens not in that higher layer of the atmosphere, which was the stratosphere being destroyed by CFCs, but what happens in the first layer, which is the troposphere in the polar regions. And that's important to distinguish because they're 2 different phenomena, but similar in terms of what actually governs the chemistry, okay? So today, in the atmospheric science community, since the late 1990s, and even before that, people have gone to the polar region, the Arctic especially, because it's easier to get to just measure it and see where all the stuff we make in the lower and mid latitudes, how it affects the polar biosphere, right? And a lot of you all do some of that kind of work, whether it's from remote sensing or straight field measurements. So today, I will talk about specifically iodine in the polar regions, all right? And even the mechanism that won the Nobel Prize, people knew that iodine catalytically destroys ozone, right? So people knew that long before. But before actually getting into the actual story, I'd like to give you a little bit of background on why this is important, why studying ozone is important. And this is just a schematic diagram representing the layers of the atmosphere. This is the first layer, usually about, of course it's latitude dependent, but the troposphere, in the lower part of the atmosphere, you have ozone, where it's an oxidant, and we know oxidants are not good for you. It's one of the components of smog, all right? And so it's for bad air quality if the ozone levels are too high. And then we have, oops, I'm not used to using these things here. Oops, sorry about that. We have, in the middle of the troposphere, we have ozone. Yes, I think I'm gonna, my fingers are big, so that's the problem. So I'll only change it when I have to go, but I'll point, because my fingers have. So anyways, so in the middle of the atmosphere, it's a cleanser, so it's like a broom, because it reacts with a lot of air pollutants. And then in the upper part of the troposphere, it's synonymous to methane, CO2 as a greenhouse gas, and so forth. And then in the stratosphere, as like I said, if we didn't have it, we would not be living here because it protects us from extreme UV radiation. And I call this the Mike Tyson, one of the Mike Tysons that supports life, right? And the reason being is that you can, if you compressed all of this to, you integrate it globally, all the ozone, and compress it to the surface of the Earth, all around the world, its thickness would be just the thickness of a penny, right? So that's how much ozone we have in our atmosphere. So it's very important. So it packs a big punch. Now, how has ozone changed since the pre-industrial revolution? So in the context of this, you have to keep in mind that about 35 to 55 ppb on the study you look at, meaning that human beings really start to feel funny, after about an hour or two in environments above 35, 55 ppb, and living things such as plants and stuff start to be detrimentally affected around concentrations like this. So this is a huge increase since the pre-industrial revolution, and this is background concentrations, right? Places in remote regions. So that's it's not good. And then it has a multitude of effects, such as health effects, which have been documented. It causes respiratory problems. It contributes to mortality rate. And one of the areas that's really being affected by this now, one would know, is Eastern China. Its mortality rate is almost increased by 30% for people living these kind of regions, right? And that's very significant. And it affects plant growth because oxidants destroy the tissues of plants. And someone went a step further and used the Monte Carlo linear regression study at Goddard Space Flight Center to look at the monetary aspect of the destruction of crops, directly correlated to ozone. I don't know all the details, but this is all I know. He came up with this figure, and that's pretty sizable, right? We would all like 15 billion, I think, at least spread it out. So businesses don't like that. And like I stated previously, it's one of the greenhouse gases after CO2, methane, well, water vapor, of course, CO2, methane, etc. And it also has two distinct sources, natural sources from lightning in the upper atmosphere, breaking down molecular nitrogen, which then reacts with atomic oxygen, and then also anthropogenic sources as well, primarily through biomass burning, automobile emission, and industrial sources. Given all these problems, people always talk about the bad stuff, everything's bad, so we need money to go solve it, right? And human beings, although we complain about problems and how we're trying to solve them, and nothing is ever truth, but we still are innovative. And globally, I just put this up here to show you how humans can be innovative. We have, in conjunction with the European Space Agency, NASA, and also Russia and Asian agencies, especially Japan, created a suite of satellites that we all know circle around the Earth to measure, try to understand the composition and why things happen, right? And EPTOMS and URS, Upper Atmospheric Research Satellite, Total Ozone Mapping Spectrometer, and Aura satellite. There's three satellites that I've, primarily Aura as well, that I've used satellite data products to try to get a better understanding of data products of ozone and how they correlate to prediction and models and so forth. But the main take-home message when you look at these two is that this satellite was launched in 2004 from Vandenberg Air Force, similar to the TOMS, but these two really, this satellite actually transformed how data products get and fed into models to give us ideas of prediction and simulation. And why is that? Because prior to aura, all data was just column measurements, right? So they integrated from the top to the atmosphere, and it's, of course, it's very hard to really say a lot on a really different resolution, especially smaller resolution. And this was the first satellite to actually give vertical profiles of ozone, and with pretty decent resolution, 5 kilometers to 8 kilometers, depending on the limb or the nadir view. So I was very happy to get experience on handling satellite data products at JPL. And I just wanted to show this model, graph. This is a graph, obviously, of ozone versus Dobson unit versus time of year. And this is a model fit, and you see the recovery there. And of course, those have huge bars, but this is, in general, we know that the ozone layer is recovering. And these are explicit plots of satellite data. You have the total ozone mapping, and you have various versions of the Nimbus. They had Nimbus 1 all the way to Nimbus 7. And these oscillations just represent the maximum amount of ozone that you would have in any particular time would be when Antarctica is experiencing its winter, right? And then when it's in the summer, obviously it's less because Antarctic ozone actually sometimes goes to 0. So hence, when you integrate the entire column of the globe, you get this really low value. But the Arctic is not so significant, right? And so people have done various modeling predictions, and just to get back at this, these error bars are very huge here because why? Humans, of course, we can't really predict the future so well, even with the most fanciest science. So there you go. But we do know that the Nobel Prize winners were actually right, and that human beings can really do good, especially when we do understand the science and how it can actually affect globally what we do practically. And this is a plot of concentration versus time of year of the halogen occultation experiment in the UARS. And this just shows you a reservoir species, which usually forms from CFCs after they get destroyed. So it gives you an idea of this time period, 1995. The Montreal Protocol was around here. 1995, they win the Nobel Prize. Of course, it's not just going to go down because people say, stop using it. There's some lag period, but see that it's leveling off, even in this fine resolution concentration plot. And the aura, the same version of that instrument, but on the latest satellite. That was on the previous Nimbus. Total ozone mapping spectrometer. You see the same thing, but now you see a downward trend, right? As you pass further years. And I could have extended this plot, but it continues downward. So that's a good sign. What's up?
This time period after one, the slide before?
Oh, yes. I believe, yeah. Yes, yes. Yeah, and you could see there, yeah, exactly. And the resolution is a little bit sparser here. I mean, a little bit more years, and this is finer resolution here. Yeah, so it's good. It's a good sign. All right, so some of the uncertainties on ozone, predicting the abundance of ozone hole is this upper atmospheric, lower stratospheric exchange. They range from 25 to 50%, people using tracers, right? So, and the full recovery of the stratospheric ozone hole. Remember I said that there's this huge uncertainties on the tip, and it's kind of, it's hard to do. And that's primarily driven by the fact that the world is huge, of course, and there's so much data we have. But the Earth is a heat engine in some ways. So as things get warmer, people believe that you're moving air faster towards these different cells, whether they're in the northern hemisphere or the lower hemisphere. And that abundance, there's uncertainties each of these as well, but this propagates with, they don't really have a full understanding of how that mass will change, especially on long-term timescales, right? So that's really the core of the uncertainty in terms of the ozone hole recovery. How do these dynamical cells move air, especially ozone, embedded with chemistry, really, where's all that ozone going to be? Is it going to be mostly in the northern, the northern polar region, southern polar? So that's a tough question to answer, but it represents one of the uncertainties. Another uncertainties as well It has both natural and anthropogenic sources, but really quantifying the contribution of each compared to each other, right? People come up with different values and they model and et cetera. And this is, I think, is very interesting, a really interesting one. We know the Asian monsoon kind of governs about 2/3 of the weather patterns we have on Earth. So if you have warmer temperatures, how does that affect the cycle of precipitation, chemical composition? And also in the North American monsoon as well, you see potential similar uncertainties in predicting ozone based on these dynamical effects. And variations in precipitation. Students ask me all the time in New York, what's going on? Global warming, is it gone? Et cetera, et cetera. But I tell people, look, if you take a glass of water and then you boil it, where does it go? It goes up in the atmosphere, right? So that's the simple way I answer people's questions, right? It's getting warmer, so it's going to go somewhere, right? And then, you have some dust maybe from Asia is always coming, and then you get condensation nuclei, and so it's not surprising, right? And people have been observing this for the last 2 decades, right? So, but I wish the western part of the United States was getting it. Okay, so we have a lot of uncertainties, or some uncertainties with ozone, but today I'll just talk about processes governing polar ozone depletion events. Why it's important, previous and our approach to solving this problem, and I'll go through results and conclusions and ongoing and future research, and I have to thank you all for listening to me. Yeah. Okay, so since the late 1970s, people have observed this ozone depletion events, right? Both in the Antarctic and in the Arctic, in the troposphere, but people never understood why. But researchers in Canada, some of my collaborators, they went in the field and decided, these lab experiments, they always have this kind of anti-correlation, these halogens have this anti-correlation with destroying ozone. I wonder if we can see the same thing in the field. So they developed machines, instruments to take it out in the field and to see if they would observe just that, right? And voila, what do you see? This is polar springtime in the Arctic. You see this anti-correlation with bromine and ozone, right? So they assumed something may be directly correlated there. So in the Arctic, this kind of was the first plot by Baradal to show that ozone was being destroyed catalytically during polar springtime, where ozone levels were reaching not zero, but close to it. And before I keep on going, so the Arctic had a consensus, I'll go back here, that bromine chemistry was governing the destruction of ozone, okay, in the troposphere. Now, people, for whatever reason, I guess not that many people went to do similar observations in the Antarctic. Maybe it was lack of funding, but the situation is what it is. So people just assumed that the same thing was going on in Antarctica. Why? Because you have ice there. You have a bunch of ice in the Arctic, a bunch of ice in Antarctic. Hey, it might as well be the same thing, right? But not necessarily the case. But people measured bromine. Yeah, so people measured bromine catalyzed destruction in the stratosphere, over the Arctic as well. And prior to 2007, I was fortunate enough to meet one of my collaborators. Only integrated measurements of halogens were measured in Antarctica, right? Not field measurements necessarily of measuring the same thing Baradal did, but just integrated measurements. We're trying to look at the same thing. But if you think about it, you can't, that's like comparing apples and oranges. If you can't compare someone going into the field and saying something and then use a satellite that does a column measurement and come to the same conclusion. So my collaborator, his name is César Lopez et al., he published a paper in Science that showed just this, that ozone contributes to about twice the destruction of compared to bromine over the same given time period. So he did 6-month measurements using a technique called max DOAS, differential optical absorption spectrometry, which is collecting light and looking at the excitation states of different species to get a grip on the concentration, and found out that iodine was the major player here, not bromine, right? And so people were like, oh, how come we never observed iodine in the Arctic? Why is that? All right. So when I was doing my postdoc in 2007, he and I just happened to have this, I would say, a very fortunate crossing of the minds. I was very familiar with his work. He was familiar with my work. And we fortunately became office mates. And this paper derived from a simple question from Alfonso. Can you solve this problem? I know you did a lot of ice chemistry and physics for your thesis. Think about it. No one knows why we measure so much iodine in Antarctica, and no one knows why it's never been measured in the Arctic. Why do you think that's the case, right? Of course, I did a lot of research, and that'll be the rest of the talk. But these two plots just really show the catalytic destruction based on uptake coefficients. Of course, if you have a larger uptake coefficient, of course, it'll be destroyed faster because it's settling faster at different halogenated, iodinated species. But the main thing is this plot, that ozone is being destroyed twice as fast compared to bromine chemistry. And that's the take-home message of his paper. Okay, so just to reiterate, this paper, which was originally written in 2007, and is coming out next week. Yes. That's can we explicitly simulate polar tropospheric ozone depletion events? And if we can, what does that teach us about the Arctic, maybe, versus the Antarctic? You know, why have people not measured iodine up there, right? What's the difference? Okay. So using a deductionist method, we have to look at sources of iodine, okay? And one of the sources are, of course, halocarbons, but there's a problem with these halocarbons. It's either their concentrations are too high, so imagine if this was too high and then you had this lifetime as a minute, then we know we'll get a bunch of iodine there, right? But obviously that's not the case, it's just that it's too long. So even with halocarbons that have the amount of concentration that would actually give it, the lifetimes are too long. So you don't get anything from those. And it's just the converse of this. You can have halocarbons, what their lifetimes are too short, but their concentrations, of course, are just way too low.